Yeah.
Oh, fun time's over.
I'm back. Mitra laughs. Yeah, like the last thing they want to hear, right?
Welcome back.
Thank you. My computer ran out of battery, and it was plugged in. It's just plugged into this this USB port that's broken. Anyhow, so now let's see. This is a bunch of pain in the butt now. So you guys can see this. So moderator scatters the neutrons and slows them down, but does not absorb them. So I want somebody to tell me what type of nucleus can scatter a neutron and take away energy. And I want you to, and I'll boil this down. I'll boil this down to the difference between hydrogen nucleus, a proton, and a U-238 nucleus, right? Which weighs out of 238. One weighs 1, right? 1 AMU, right? Now a neutron weighs 1 AMU, right? And if it hits a 238 nucleus, it's going to bounce off, right? And some of the energy is going to transfer to the U-238, right? And some of the energy is going to transfer back into the into the neutron when it scatters along its way, right? Now, imagine that neutron hitting a proton, which is the same mass. Little drama happening out here, sorry. And then when that guy bounces off, it'll be like billiard balls, right? Billiard balls are the same weight, same mass and size. And when one billiard ball hits another, the energy gets divided, or that momentum gets divided into the two entities, yeah? So, in which case is there more momentum transferred to the moderator? When the moderator is hydrogen, or when the moderator is U-238? Okay. Let's do a thought experiment there. Imagine 2 billiard balls. One of them is made of normal billiard ball material. The other one is made of lead. So it's a heavy billiard ball, right? And you shoot your cue ball into the first one. And you know how when you hit a ball dead on, your ball stops and the other ball takes off? Right? So what if you hit this heavy ball dead on with your cue ball? What's going to happen?
Your cue ball bounces back.
Yes, exactly. Exactly right. So the amount of momentum that it loses to the heavy ball is less or more than the amount of momentum that it loses to the light ball.
It'll be less.
Right. So, which is a better moderator? Water or U-238?
Water?
Water, because, just recapitulate what I just said. Your answer is correct.
Water because not or more of the momentum or sorry, yeah, more of the momentum is lost compared to if it were to crash into the U-238.
Exactly right. Exactly right. Now, water is a pretty good example of a moderator. It's actually an excellent moderator. There's some small capture cross section for neutrons from protons, right? If a proton captures a neutron, it becomes what? You've all used them. You've used them. You've had this stuff in a pipette in your hot little hands, I guarantee. Yes, you have, Adam.
You said when a neutron captures a proton, or a proton captures a neutron?
Yeah, proton captures a neutron, right? What's P plus N? I mean, that's going to confuse everything.
Is it just hydrogen?
Yeah, it's hydrogen, right? But it's a particular type of hydrogen, right?
Oh, deuterium?
Oh my God. Man is correct. Right? And so protons can capture neutrons and become deuterons. What do you think, Calvin? Am I full of it or am I not full of it?
I believe you.
Can I repeat what I just said?
Sorry, I'm really having a bad headache.
Oh, I'm sorry. I'm sorry, buddy. Trust me, I know what you mean. So this too shall pass. Thank you for being here. Let me pick on Carla.
So question, Dr. Terrell.
Yes.
So when they're making like internal standards for mass spectrometry and they're using deuterated hydrogens, how do they get, so you're saying they use a neutron leaving group, if you will, and have the hydrogens capture that?
Okay. So mass spectrometers don't do anything to the nuclei.
No. I know
Yeah.
that, but
Okay.
I know from experience from mass spec, we use internal standards, which have typically deuteriums or carbon 13s. Do they generate those?
They're deuterated or carbon 13 substituted.
Right. How do they generate those? Do they do it with where they get the extra neutron?
Exactly right. Exactly. Good question. So I don't actually know. I believe that most deuterium is actually distilled from pure water. So H2O is, HDO is distilled from H2O. You think, how the hell do you do that? Well, it's not easy. But there's like 1% deuterium, right? So, a couple percent of the water have a deuterium substitution. And there you go. And I don't know about C13. I don't know how they do that. And it's not unreasonable to think that you could use a reactor and use that neutron beam and capture neutrons and slowly build up these heavier nuclei. But I don't think that's how they do deuterium, and I don't think that's how they do carbon.
Yeah,
because carbon
really expensive.
Yeah, I think carbon has a very low capture cross section. So even though C13 is fairly abundant in the universe, I think it's quite hard to make from C12 using neutrons. The reason I say that is the second best moderator in the world after D2O actually is the best moderator. Second best moderator is pure carbon 12. So, so I think that C13 is probably also natural. C14 is made in the upper atmosphere, however. What is C14 used for? No, not NMR. C14 is used for carbon dating. And I'm not talking like speed dating, I'm talking about carbon dating. I've only had one date in my entire life. Okay? This is a portrait in cowardice. But fortunately it was with a good woman. So she's still with me.
1 for 1 is not bad.
1 for 1. That's exactly that. 1 for 1. I'm 1-0, man. No. So but yeah, carbon dating is where you measure the time since something died. Right? And that's the time since it was actively exchanging carbon with the atmosphere. And in the upper atmosphere, things happen to carbon atoms that are from highly energetic particles that enrich the carbon-14 composition in the CO2 in the atmosphere. I don't know, it could start with oxygen for all I know, or nitrogen, but there's C14 comes from the atmosphere. So when something dies, it goes underground and it stops exchanging C14 with the atmosphere, the abundance of carbon-14 starts to decay slowly. Does that make sense? This is nuclear chemistry, man. This is nuclear chem 101. So Carla, if I die and you measure the carbon-14 abundance in me, and then you bury me, and 10 millennia later, they dig me up and they measure the carbon-14 abundance in me, who will find more carbon-14, you or future Carla?
Me.
Yes, exactly right.
That's the like
Then-
Half-Life stuff, right?
Right. Because my carbon-14 will decay away. Because, and why is my carbon-14 now abundant, Adam?
Because it's in the atmosphere and you're in the atmosphere.
Right, exactly. What do you think, Kenya? Are we all getting A's today?
You're all getting A's today.
I like it. I'm actually in a good mood. This is weird. This is unexpected.
I'm happy for you.
Just kill me now, please.
You should be happy every day,
Oh God. Oh no.
Flex
No,
up.
No, don't get my
You don't
hopes
like
up.
being happy, Dr. Terrell?
Of course I like it.
You don't like feeling good?
Just don't get my hopes up. I'm gonna be all attached. Then I'm gonna get depressed. Okay. Shut up, Roger. My wife's telling me to shut up and move on. Okay. So, oh, I'm sharing neutron versus. I thought I was going to share my other screen. Okay. So, let me see if I can find my cursor here. So Mossbauer was looking for the Mossbauer effect paper that came out in the 40s. Was just on an effect where neutrons are emitted with no recoil loss. Oops. Oh, that's weird. EU neutrons emitted right? So that's kind of strange, right? Because when you think about a momentum conserving thing happening. I mean, that is like the golden rule in physics, that momentum is conserved. You know, angular momentum, and linear momentum, and whatever momentum, right? Spin angular momentum is conserved, right? But Mossbauer, he found that let's see. Well, he found that there were certain cases where neutrons were emitted with no loss in energy. And in that case, it's so funny, Adam's wife is running by.
She's checking to make sure we're not boiling over.
I love it. I love it.
At least she's not in her onesie.
Oh no, nothing like that. That's oh man, I'm gonna get in trouble even thinking about that. So, Mossbauer effect paper with neutrons emitted without recoil loss. Let's see. Right. So Mossbauer found out that this happened, right? And it turns out that the momentum is conserved, but the momentum is transferred to the entire crystal of nuclei that emitted the damn thing. I know it's boring, but it's like if you have like a diamond or something, and one of the atoms is C14 and it shoots out a neutron or something, right? It's possible that the entire diamond can absorb can conserve the momentum, right? So in that case, almost no momentum is lost to the neutron. So it's sort of like a Bose-Einstein condensate problem where the entire entity acts like one thing. You know, all of the atoms together, they share the same quantum properties. So the crystal absorbs the momentum, right? And it wasn't long after this that it was realized that if you could have recoilless neutrons, you could also have recoilless gamma rays, right? So normally we don't think of gamma rays as having a lot of momentum, but or if any photon is having momentum, but they do, and it's like something over, it's like E squared over C squared or something like that. You know, you divide by C squared, so you cut it down by a factor of 10 to the 16th. But gamma rays are so energetic that they lose a substantial fraction of their own energy to transferring the momentum to the nucleus. So when a nucleus emits a gamma ray in that direction, the nucleus recoils. Unless the nucleus is in a crystal, and then there's a certain probability that the gamma ray can come out recoil-free, recoil-less or recoil-free gamma rays from crystals. You know, I don't actually know if you say have to have a crystal, but that's how it's sort of explained, right? So, if you can have a recoil-free gamma ray, then you can have, and this gamma ray is emitted by a nucleus where the final state of the gamma ray emission is the ground state of the nucleus. So let me docu-chem here real quick. Where is my thingy? Meeting controls. Where are the meeting controls? Oh, I see. Your screen sharing. New share. Document. So, there we go. There we go. So, wait, it didn't, okay. Share again. There we go. So, so if you have a nuclear state, right? You know that you're familiar with electronic states, right? We talked a lot about them during the fluorescence debacle or unit, right? And electronic states, you know, they're separated by photons, right? So you can have, excited state and then ground state, and then you can absorb a photon and emit a photon, right? And the same is true for nuclei, right? And the particular one that we're thinking about right now is that there's a decay chain that starts with cobalt 57, and it undergoes electron capture to make iron 57 in an excited state. And this iron 57, then it relaxes by the emission of, I think there's 2 gamma rays, right? Gamma 1 and gamma 2. Gamma 2 is, it's like 14 keV, right? 14,000 electron volts in this gamma ray. And this is the second of 2, and this makes ground state iron. And so the trick then is, can you do resonant absorption of this 14 keV gamma ray by iron 57 nuclei, right? And so the idea of the recoil loss would normally completely mess that up, right? Destroy resonant gamma ray processes, right? Because because the energy of the excited state to the ground state is going to go partly into gamma ray and partly into recoil. Oops. And so now this photon, if it hits another iron 57 in the ground state, it does not have enough energy to promote that state, and so it just passes right through. That's weird, isn't it? That, like, light, if it can't interact with stuff, it just ignores it. You know? And there's weird exceptions to that, like Raman scattering, you know? But mostly this is the rule. So, however, if there's no recoil, right, from the excited state to the ground state, then this photon that comes out of there can then be absorbed and make a ground state into an excited state, right? Which will then within 100 nanoseconds will re-emit, right? But it will re-emit in random directions and with high probability of recoil loss, right? So one of the tricks is to get a source of iron 57 or cobalt 57, and then have a collimator
Could you move the paper up, please, Dr. Terrell?
Absolutely, sorry. Yes. So this is the 57 cobalt source. This is the collimator. And who knows anything about optics? So optics depend on the refraction of light, right? And so that means that the refractive index of this stuff has to be, 1.4 or whatever, and then that bends the light ray and et cetera. But for X-rays and gamma rays, they basically don't interact with normal matter very much, And so the refractive index of glass to a gamma ray is 1.001 or something like that, or to an X-ray. So you can't really use lenses for X-rays or gamma rays. So you use caveman optics. And caveman optics, the collimator is a long lead tube. Right? So this is the caveman optic here. Right? And then you have your target, right? And your target is iron 57. There's your absorber. And then you have a detector for the gamma rays. And gamma detectors are they're like sodium iodide. They're these big old crystals of sodium iodide, and the gamma rays go in there and they bounce off the nuclei, and they dislodge sodiums and iodides, and the whole thing glows. So it's really a combination of sodium iodide and a normal photomultiplier tube. And so if you do this experiment, you take cobalt 57, long lead tube, and put iron in there, you have a problem, right? Is that you can put the iron in the way and then it'll absorb some of the light. But you don't have much information. So how do you do spectroscopy then? How do you vary the energy? How do you vary the energy of a gamma ray, right? So enter the gamma ray spectroscopy paradigm here. And that whole idea here is that you can use Doppler shifting. And the one of the weird things about this this excited state iron 57 the excited to the ground state transition is that it is an extremely well-defined transition energetically, right? So you may ask, Dr. T, where does the line width of a gamma ray come from? What is the origin of line width in gamma rays, for example, of this nature, right? And the answer is uncertainty principle. And let's see. The Planck's constant, or the uncertainty principle here says that delta E times delta T is approximately equal to H bar, right? I'm almost certain it's H bar. So if it's not, then we can, no, I'm pretty sure it's H bar, right? So H bar is equal to 6.6 times 10 to the minus 16 electron volts times seconds. I'm going to use EV here because, I don't know, the gamma rays are in EV, so, right? So the delta T is the lifetime, it's the average lifetime of the excited state. And I would love to think about this at some point in time because, you know, this excited state lifetime does not come from a Gaussian distribution. It comes from a Poisson distribution. So I don't know, like, I don't really get it, but but suffice it to say here, if we just say, if we substitute T1 half for delta T, right? Then delta E is equal to H bar over delta T, which is equal to 6.6 times 10 to the minus 16th EV seconds over 10 to the minus 7th seconds, right? This is the excited state iron 57 half-life.
Dr. Terrell, could you move it up again, please?
Yes. I'm going to intentionally do this just so somebody says something occasionally. It's like, I think, oh my God, question. And no, I just have to move the stupid paper again. Okay, to the project. So T1/2 for, let's see here, and then T1/2 for 57 Fe star is about 100 nanoseconds. So it's 10 to the minus 7 seconds, right? So this comes out to about 7 times 10 to the minus 11th, the EV, right? Now, what is the energy? So E is about 14 times 10 to the third EV. Delta E is 7 times 10 to the minus 11th EV. So the sort of the one way to express this line width is relative energy uncertainty. And that will be delta E over E, which will be about 7 times 10 to the minus 11 over 14 times 10 to the third, which will be about 1/2 times 10 to the minus 14. Or about 5 times 10 to the minus 15. And that's a unitless value there, right? So when you're thinking about the world of chromaticity, right? You can think of it like here's the amplitude, and here's the let's use frequency because it's directly proportional to energy right here.
Dr.
So
Carol,
sorry.
the graph is
Curses. I'm just kidding. So yeah, amplitude as a function of frequency, right? You might think, well, a narrow line might be a UV atomic transition, right? And they are also significantly uncertainty broadened. They're also Doppler broadened. So there's both of these effects. There's a Doppler plus uncertainty broadening there, but they're about 50 nanometers over, say, 200 nanometers. Okay, so I'm using nanometers instead of energy. How can I fight my way out of this paper bag? No, not 50, not 50. They're 0.05. 0.050. 0.050 nanometers, right? Over 200 nanometers. So let's just say that this is 5 times 10 to the minus 2 over 2 times 10 to the plus 2. This is about 2.5 times 10 to the minus 4. Right? Sorry, that's kind of small there. But 2.5 times 10 to the minus 4 for a UV photon. And and there's also Doppler broadening on top of that, right? But actually, this is the phenomenological one. So the uncertainty might be a little bit smaller than that. But compare that to the uncertainty broadening in a gamma ray here, and it's staggeringly, it's 11 orders of magnitude different. So it's 100 billion times more monochromatic, right? So if we had if this was a 50 nanometer wide or 0.05 nanometer wide ultraviolet line, the corresponding gamma ray would be a perfect spike, right? It would be 0, spike, and then back down to 0 almost instantly. So this is the UV line. This is the gamma line. So it is possible then to do spectroscopy on this gamma line using Doppler shifting. I'm going to be done in about 15 minutes. So, where was I here? So basically, I should probably just show you the some examples of Moss power. Come on. Okay. Okay. So let me figure out here. Oh yeah, and then next time we can talk about the Pound Rebka experiment, which is super cool. Pound Rebka is a massive victory for general relativity. And it uses Moss power, which is a completely quantum thing. So this is how tightly interwoven our universe is. So let's see, broadening of spectral lines, blah, blah, blah. There's our periodic table. I'm trying to put together a decent talk on this subject. Right? There's the s orbitals, right? Which we're going to talk about in terms of Moss power spectroscopy. There's Pound Rebka. Here's Moss power, right? So what turns out then, what happens is that you can look at the absorption of these gamma rays by a sample as a function of the velocity of the source relative to the sample. So in this spectrum up here, you can see there's there's 6 lines here, and this is the Moss power spectrum of iron 57, and these are different spin states of the iron nucleus. And this is these are nucleon spins, things like proton and neutron spin states. I don't even know, to be honest. But look at these meters per second. Like this is -1 centimeter per second. And that tiny bit of velocity, relative velocity, between the source and the absorber is enough to completely wipe out this recoil-free absorption phenomenon for iron, for this iron nucleus. Yes, you have a question, Richard. What is it?
I just want to know why.
Yeah, cool, huh? I love it. Why? Why, damn it, why? My wife is tired. My wife and son are with me today. They're in the office, and they're both exhausted. And they're wanting me to get on with things. I don't know how to take away the stupid background. So let me see. How many? What do you think the Doppler shift is on a photon going 1 centimeter per second?
I mean, nothing, right?
Nothing. Nothing. How do you calculate Doppler shift? Well, it's the relative velocity. It's the velocity relative to the speed of light. And 1 centimeter per second relative to 10 billion meters per second is nothing. You know? Oh no, I'm sorry. 300 million meters per second. Sorry, that's the speed of light. 300 million meters per second. So let's calculate the speed of light in meters per second here, in centimeters per second. Let's see. Okay, so let's see here. I actually had the Doppler shift equation for light down, but it was a little bit weird. And I think I didn't understand it as well as I thought I did. It had 4 terms. It was kind of like, what? Didn't it just do? But let's just think about this in terms of, you know, in some sort of simple limit, right? So we're talking about 1 centimeter per second of Doppler shift. And the speed of light is 3 times 10 to the 8th meters per second, or 3 times 10 to the 10th centimeters per second, right? So this is literally 1 part in 10 to the 10th, or 1 part in 10 to the 11th. If you're talking 1 millimeter per second, this is centimeters per second. This is millimeter per second, right? And so we kind of have to go back to this prior conversation about how narrow these lines are. And 7 times 10 to the minus 11th EV is the line width, you know, and relative to the actual energy, it's 5 times 10 to the minus 15, right? So in this case, we've got you know, 1 time 10 to the minus 11th, right? That's a 1 millimeter per second Doppler shift. And then the natural line width of these guys is 5 times 10 minus 15, right? So 10 to the minus 11th here. And then the natural line width is 10 to the minus 15th. So that's kind of why this can be done, because we're winning by 4 orders of magnitude in this case. So now there's things about this that I don't really understand. Does the absorption recoil matter, right? And I'm pretty sure it does, you know? You know, it's like there's this, it's like, you know, there's this nucleus and it fires off this photon. The photon goes over here, and then it gets absorbed by another nucleus, right? And this nucleus gets pushed that way, and that nucleus gets pushed that way, right? But probably there's recoil-free absorption processes as well as emission processes. And so probably what the fraction that we're seeing in the Mossbauer experiment is the recoil-free fraction. So what we're going to talk about next time is called the Pound-Rebke experiment. The Pound-Rebke experiment uses Mossbauer spectroscopy to weigh photons. To weigh massless photons. And so basically this is to compute their Doppler shift as they move up in a gravitational field. Right? And then we'll talk also a little bit about how does chemistry affect Mossbauer signals. All right. So I know that I'm 10 minutes early, but if I'm to get home with my life, I have to go now.
Makes sense too.
So I want to know, I know I'm boring as a professor, but I want to know how I did today, because I'm trying to make this into a unit that I teach online to the high school minions, the high school brainiacs in Cosmos. Minions, yes. Mitra tells me I'm not boring now, but just wait until like I try to have a conversation with her. It's like, oh, you're so boring. Okay, I better shut up. Bye. I'll see everybody next time.
Bye.
Okay.
Happy Thanksgiving.
Happy Thanksgiving.
Happy Thanksgiving.
Bye.
Bye-bye.
Happy holidays.
Happy holidays.